So here we record conics and linear subspaces. So conics and linear subspaces. So say the conic in P2, this x square equals to yz, is isomorphic to P1. So we have to construct a map from P1 to x, where x is this conic, x square is equal to yz, and this conic lies in P2. So this map is given by uv goes to uv comma u square comma v square. So you can multiply and check. X square is u square v square is equal to yz, which is u square times v square. So the three coordinates of x are x, y, z. Now this map is well defined because we have three homogeneous polynomials uv comma u square comma v square, which are of the same degree. And second, if u and v are not both simultaneously 0, then uv comma u square comma v square are also not simultaneously 0. So that gives us a well-defined map. Now we have to define a reverse map in the opposite direction from the conic x, which is embedded in P2, to P1. So first notice that every point of x, obviously x lies in P2, belongs to two sets. So it belongs to one of the two sets. So either it belongs to the open set u1, which corresponds to y not equal to 0, or it belongs to set u2, which corresponds to z not equal to 0. Now this is because if both y and z are 0, then x square, which is equal to yz, is also 0. And this is not allowed. Obviously, all three coordinates cannot be simultaneously 0. So the reverse map, say var phi, you go to P1, you obviously on U1 you take to x and y because y is not 0. And on set U2 you take x comma z because z is not 0. Obviously you have to make sure both the coordinates do not vanish. So we get map from P1 to x and x to P1, and you can see that these two maps are reversed to each other, and therefore there is an isomorphism. Now I just want to make an important remark. So you have this projective transformation from P2 to P2. So here I is the complex number such that I square is -1. So this projective transformation will carry a irreducible curve of degree 2. So this is an irreducible curve of degree 2. This is carried to a conic. So the remark basically says you have a projective transformation which will carry any irreducible curve of degree 2 to a conic. So this is a fun fact. That is, an irreducible curve of degree 2 can be moved to a conic in P2. Now let us talk a bit about hyperplanes. This we have discussed multiple times, but let us do some more activity with this. So a hypersurface in Pn of degree 1 is called a hyperplane. So that is this hyperplane is defined by a homogeneous polynomial of degree 1. So now we define a linear subspace. Non-empty intersection of hyperplanes is called a non-empty intersection of hyperplanes is called a linear subspace of Pn. So again, a non-empty intersection of hyperplanes is called a linear subspace of Pn. So the result we want to prove is that if Y is a linear subspace of dimension R in Pn, then Y is a linear subspace of dimension R in Pn, then Y is isomorphic to PR. So there is not much in this, it is just the interplay of definition of hyperplane. So we will prove this just by writing two equivalent definitions of hyperplane and just playing with it. So you know that hyperplane is nothing but isomorphic to Pn minus 1. So that is, it is a codimension 1. So that is, hyperplane is nothing but a codimension 1 k-linear subspace. This is from the definition of hyperplane which we have given before. So now you make a affine cone. Now affine cone you can find again, if you have forgotten, it is on page 12 of Hartshorne. So basically you add one more dimension. So now you are making affine cone out of hyperplanes. So this you can see, refresh your memory from page 12 of Hartshorne. So hyperplane becomes a k-linear subspace of this affine space. Of kn plus 1. Yeah, so you have added one more dimension, ended up in Pn, therefore you have to end up in an plus 1. So thus affine cone Y over a linear subspace X of Pn is the intersection of these codimension 1 linear subspaces, that is hyperplanes, which we have now converted into cones. So the affine cone of Y comes from intersection of affine cones of hyperplanes. So thus Y itself becomes a k-linear subspace of an plus 1. So Y itself becomes a k-linear subspace of this an plus 1 k. So now you just change coordinates by linear transformation and you have the coordinates of Y like this. Yeah, where R is dimension of Y minus 1. So now it is just semantics. You convert this into projective space of dimension n, and then this first R tuples, you just extract them and they are isomorphic to PR, as you can see.